So here's the setup to the heat equation problem. Imagine an infinitely thin, stiff wire of some length L. This imaginary wire exists in a theoretical world where there's no heat loss. So if the wire is at room temperature, then the wire will remain at room temperature. If the wire is at 100 degrees Celsius, then the wire will remain at 100 degrees Celsius. Although there's no heat loss in this world, there is heat transfer. So if one end of the wire is heated and the other end of the wire is cooled, then the heat will transfer through the wire at some rate over time. That heat transfer rate will depend on the initial temperatures, the length of the wire, and the material properties of the wire. Given this setup, we're going to give this wire an initial temperature profile where the left half of the wire starts at a high temperature and the right half of the wire starts at a cool temperature. Over time, the heat will transfer along this wire. Your mission, if you choose to accept it, is to calculate the different temperatures along this wire at any time t. If you choose to accept this mission, can you solve it in Julia by using the DifferentialEquations.jl package and Pluto? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. I'm assuming that you've watched the first 12 episodes of this series, so I'm assuming that you know how to use Pluto notebooks and that you know the basics of the Julia programming language. I'm also assuming that you know how to use the DifferentialEquations.jl package in order to solve first-order ordinary differential equations, second-order ordinary differential equations, systems of differential equations, and stochastic differential equations. With that said, let's get started. Let's start by firing up the Julia REPL and launching Pluto. Next, let's create a new notebook and title it One-Dimensional Heat Equation. This is optional, but I'm going to customize this user interface like I did in the first tutorial. Let's save this file by using the Save Notebook bar at the top. For this tutorial, there are a lot of reference links. I'll be referring to them throughout this tutorial, but in the interest of time, I'm just going to copy and paste these links. Next, let's add a few packages. These are the same packages that we've been using throughout this series, so you don't need any special packages in order to solve the heat equation problem. Now that everything's loaded, let's describe the problem that we're trying to solve. Today's heat equation challenge is inspired by a really great 3 Blue 1 Brown YouTube video that he made on partial differential equations. As one of his motivating examples, he uses two bars that are at different temperatures that come in contact with each other. One bar is at 90 degrees, and the other bar is at 10 degrees. He then animates the resulting heat transfer over time between the two bars to provide a high-level conceptual explanation about how the heat equation works.
Wow!
We're not going to try to recreate his amazing animation, but we will be creating an interactive simulation model that we can use to replicate his results. Although the 3 Blue 1 Brown video was made relatively recently, the heat equation challenge can trace its roots back 200 years to the year 1822, when Joseph Fourier published his work on heat flow titled The Analytical Theory of Heat. At first, this problem doesn't sound that difficult, right? It's asking how temperature changes over time, which sounds like an ODE. But upon closer inspection, problem is really asking how temperature changes along the wire at any time t, which is not an ODE. So in order to solve this problem, we need to understand how temperature changes with respect to both time and space. This is not an easy problem to solve. Welcome to the world of partial differential equations. An ODE defines how something changes with respect to something else, usually with respect to time. A partial differential equation, or PDE, defines how something changes with respect to two or more things at once. So the heat equation is a PDE because it defines how temperature changes with respect to both time and space. For the heat equation problem, quote-unquote space can be defined in 1 dimension, 2 dimensions, or 3 dimensions. For simplicity, we're going to look at the one-dimensional space only, which we will represent by the variable x, which is a position along the x-axis. The really curly lowercase d indicates a partial derivative, which you can display in LaTeX by using \partial. That superscript number 2 indicates a second partial derivative. So this equation is read: the partial derivative of temperature with respect to time is equal to alpha times the second partial derivative of temperature with respect to position. Alpha is a parameter called the thermal diffusivity of the medium. The higher the value, the faster the heat will transfer. The lower the value, the slower the heat will transfer. For example, copper, which transfers heat very quickly, has an alpha value of 111, while glass, which transfers heat very slowly, has an alpha value of 0.34. This obviously makes no sense in our theoretical world, when our imaginary wire has no thickness. But you need to suspend your disbelief and imagine that the material properties of this wire does indeed make a difference when it comes to the rate of heat transfer through this wire. So, how can we solve this? Unfortunately, there's no PDE solver included in the DifferentialEquations.jl package. Instead, we need to find a clever way of thinking about this problem. One way of solving a PDE numerically is to convert that PDE into a system of ODEs. When you think about it, you can pick any point along the wire and solve how temperature changes with respect to time, given some initial temperature at that point. That's just a standard ODE. You can repeat this process for any point along the wire. So in theory, in order to solve this problem, you would need to repeat this process for an infinite number of times. Conceptually, you can think of a PDE as a system of differential equations with an infinite number of ODEs. But for practical purposes, you don't need to do this for an infinite number of times. You only need to repeat this process for enough times to give you a reasonable approximation of the solution. A common technique for generating a numerical solution for a PDE is called the method of lines, which leaves one of the dimensions as continuous, but converts all of the other dimensions into discrete ODEs, which can be solved as a system of differential equations. That's what we're going to do in order to solve the heat equation problem. We're going to leave time as continuous, but we're going to break up space into discrete ODEs to solve as a system of differential equations. So, what's the ODE that we need to solve? The ODE that we need to solve needs to explain how the temperature changes with respect to the position along the wire. The derivation of this equation is way beyond the scope of this tutorial, but this is the equation that we need to solve. This is the equation for the second partial derivative of temperature with respect to position. I need to thank Chris Rackauckas here for providing some guidance on how to solve the heat equation problem. He was generous enough to take the time to explain it to me. For those of you who are more advanced and are interested in seeing the derivation to this equation, the link to the SciML notes on PDEs will take you to Chris's derivation of this equation. So what is this equation? Conceptually, using this equation will allow us to split up our imaginary wire into a lot of discrete points of step dx. Once we do that, we can then solve this ODE at each one of these points. The way this equation works is that it takes a snapshot of the temperature value at a given point at a given time, and then it compares that temperature value to the temperature values of its neighbor to its immediate left and to its neighbor to its immediate right. And then it calculates a new temperature value for that point for the next time step. Here, dx just means change in x. So for example, if it's hotter to the left and hotter to the right, then the new temperature at that point at the next time step will be somewhat higher than the current temperature at that point. Now that we know what we need to do, let's figure out how to translate all of this fancy LaTeX into Julia code that the DifferentialEquations.jl package can understand. One of the open questions regarding the heat equation is what do we do about the endpoints of the wire on the left and on the right? Every point along the wire is checking temperature values to the immediate left and to the immediate right relative to its own position, with the exception of the two endpoints, which only have either a right value or a left value to check, but not both. How we handle the endpoints is called the boundary condition. It turns out that there are several different ways to handle the boundaries, depending on the situation that you're trying to solve. For example, you can fix the temperatures at the endpoints to a value, like 0. Or you can wrap around the endpoints, so you treat the endpoints as if they're neighbors. But in our case, for the endpoints, we're just going to compare the temperature value of its one immediate neighbor. I know this is lame, but in the interest of time, I'm going to copy and paste this LaTeX. So our Julia function will take the arguments u, u, p, and t, which are the same arguments that we used when solving a system of differential equations. That middle equation is the ODE that we're going to solve for all of the interior points along the wire. This is just the DifferentialEquations.jl package representation of the LaTeX that we just saw. That first equation is the ODE for the left boundary, and the last equation is the ODE for the right boundary. I know these are horrific-looking equations, but we'll clean them up when we define our Julia function. We're going to have two parameters, alpha, which is the thermal diffusivity constant, and dx, which is the value of our position step along the wire, or change in x. For the left boundary of the wire, we're just going to check the temperature value of its neighbor to its immediate right. For all of the interior points along the wire, we're going to check the temperature values of both of its neighbors to its immediate left and to its immediate right. We're using a for loop here, since the number of indices will depend on the length of the wire and the value of dx. For the right boundary of the wire, we're just going to check the temperature value of its neighbor to its immediate left. I know that this function looks complicated, but it's really just a function for a system of ODEs. So conceptually, it's just like the functions that we used to solve the Latka-Volterra equations, the Lorentz system, the double pendulum problem, and the three-body problem. Now that we've defined our Julia function, let's assign the variables. U is the temperature, uppercase T, along the wire at any time, lowercase t. In order to come up with an initial condition, we need to know the length of the wire, and then we need to split up that wire into discrete points. For the length of the wire, let's just use a value of 1. Using a position step dx of 0.01 will give us a total of 101 points. 1 point when x equals 0, 1 point when x equals 1, and 99 points between 0 and 1. These values aren't dimensionless, but the unit of measure is not important here, since we're trying to build an abstract model that we can use to help us build some intuition regarding the heat equation. Let's set up some Pluto UI widgets for the initial temperatures, so we can adjust these values later. Again, don't worry about the unit of measure here, since we're just building an abstract model. For the initial condition temperatures along the wire, let's use an array comprehension to create an array where the left half of the positions have a temperature of 0.9, and the right half of the positions have a temperature value of 0.1. Using these initial settings will allow us to recreate the 3 blue 1 brown example. Notice that u_begin is a vector with 101 elements. That means we need to solve 101 ODEs. Element number 1 is the left boundary, and element number 101 is the right boundary. Because of the odd number of elements, it's split 50-51, where the first 50 elements have a temperature value of 0.9, and the remaining 51 elements have a temperature value of 0.1. We have two parameters that we need to set up, alpha and dx. We've already set up dx above, so we just need to set up alpha. Now that we've set up the parameters, we need to place them inside of a vector. And for the time span, this is just our standard setup for time. Okay, now that we've assigned the variables, we are now ready to define the problem. Since we're using the method of lines technique to solve the heat equation numerically, we can define the heat equation PDE as a system of first-order ODEs, which means that we can use the ODE problem function like we normally do. This system just happens to have 101 ODEs, which is by far the most that we've ever tried to solve simultaneously. Okay, now that we've defined the problem, let's solve it. Believe it or not, in order to solve the heat equation problem, all we need to do is use the solve function. We don't need to use any special solver. At the moment, this solution only has one row. That's because I set the default value for the ending time at 0. So what you're seeing is just the initial condition for the temperatures along the wire. There are 101 value columns. The value 1 column is the left boundary, and the value 101 column, which is off the screen, is the right boundary. Let's set up a variable uppercase t so we can plot the temperature along the wire at any time lowercase t. Let's also set up some additional variables so we can keep track of the temperature values at certain points along the wire. Okay, we now have everything that we need in order to plot the solution. For our plot, let's plot the wire positions along the x-axis, and let's plot the temperatures along the y-axis. What you're looking at is the initial condition for temperatures along the wire at time 0. As you can see, the left half of the wire has a temperature value of 0.9, and the right half of the wire has a temperature value of 0.1. If we did everything right, we should be able to see how the temperature changes along the wire over time as we move the time slider. Let's set up our control panel, and then pull down our widgets. Before we pull down the plot, let's add some markdown so we can see a sample of some of the temperature values along the wire at any time t. You can just copy and paste most of this markdown code, and then make a few minor adjustments. Now, let's pull down our plot and then hide some of this code. Okay, let's perform some analysis. If you move the time slider forward just a little bit, you can see that the temperature values in the middle change immediately, but the temperature values at the extreme ends remain unchanged. As you move the time slider forward a little bit more, the plot begins to look like a sigmoid curve. Some of the temperature values at the interior points are beginning to change, but the temperature values at the extreme ends still haven't changed. But as you continue to move the time slider forward, the temperatures at both halves of the wire begin to approach an equilibrium level. Pretty cool, right? You can change the initial conditions by moving the temperature sliders. Let's hit the reset button, change the initial conditions, and then move the time slider. You can see the impact of the material properties of the wire by changing the values of alpha. Let's hit the reset button again, then move the time slider forward slightly, and then change the value of alpha. As you can see, by increasing the value of alpha, you increase the rate of heat transfer. And by decreasing the value of alpha, you decrease the rate of heat transfer. Interesting, right? On the surface, this may appear to be a simple simulation model, but you know the truth that behind the scenes, the heat equation problem is a very difficult problem to solve. Every time you move one of these sliders, the DifferentialEquations.jl package is recalculating 101 differential equations. It's really amazing that the DifferentialEquations.jl package can take something so complicated and make it look so easy. So that does it for today's tutorial, and that does it for this tutorial series. If you made it through all 13 episodes, then congratulations! We started this series by learning how to use Pluto notebooks. We then embarked on a journey to explore the world of differential equations. Along the way, we learned how to solve first-order ordinary differential equations, second-order ordinary differential equations, systems of differential equations, stochastic differential equations, and partial differential equations. That's a lot to learn in 13 weeks. Even though I covered a lot of material, I barely scratched the surface of what the DifferentialEquations.jl package is capable of doing. So there's plenty of material left for you to discover on your own. But hopefully, this Intro to Differential Equations series has given you the confidence to pursue this subject further. There are so many people to thank for making this series possible, so I want to take a moment to acknowledge them. I would like to thank Chris Rakakis for creating the DifferentialEquations.jl package and for his many contributions to the Julia community, including his support for this channel. I would also like to thank Fons van der Plas for creating Pluto and for sharing this amazing tool with the rest of us. Thank you to all of my channel members who make these videos possible. Thank you to everyone who made one-time donations, whether it's through Super Thanks, Merch, or LiberaPay. And a special thanks to all of you for watching these videos and for sharing this incredible journey with me. I realize that folks on YouTube may be watching these videos at any time of the year, but if you're watching this video in December, then I wish you a happy holiday season. And I hope that you and your family have a happy and healthy new year.